Okay, so let's continue fast. For today, we are going to have we're going to do some examples regarding root finding. And just to drop a note for you, a homework is posted already, so I wish you're expected to submit this one by next week on Monday. And to the network that is posted, I'm just going to add a couple of more questions which are related to today's course. And I hope the reason for that is to get a better understanding of what we are doing. Okay, so so far in finding the root of an equation, we can use this knowledge in several different problems. So let's start first with a relatively simple example. And by the way, I just want to remind some of us that most of the courses, the lecture notes have been posted on Google Classroom, so you can have a look there. Okay, I hope you have already found them. And I even suggested you to go over a couple of small tasks that will help you to understand better what we are covering today. So let's see an example here. So let's assume that we have a function which is like x cubed minus 10x squared plus 5, and assume that we want to find the roots of this. I just want to see what part of the board I'm making use of. So I guess once I'm somewhere here, I should stop. And okay. So once you do the cameraman and the lecturing yourself, there are some technical difficulties, but I hope whenever the image is mirrored. Okay, yeah, I thank you for letting me know, but I'll just have to turn on the camera for a moment to see what part of the board is visible to you, okay? If something happens with the voice, please just remind me. Why is it muted? I guess my intention right now is to show the board. So, any concern right now? You said that the image is muted. What do you mean for that? At least, can you read?
It is unreadable.
Oh, how is it possible? I mean...
It is flipped.
Okay, so how can you solve this problem? I'm surprised. What about... Because probably... What about now?
Yeah.
Is it better? Can you confirm if it's okay now?
Yes, we can read this, but when you write on the table, it's mirrored. We cannot read it.
You cannot read if it's on the board?
Yes.
Kalojeni te kamera tjetër se tjetra është në rregull. Kalojeni te ajo Arbanuk, ajo te kjo presenting.
Okay, that's a good thing. Yeah, there is a problem. If you see what I see, I do see my handwriting on my own screen as flipped right, left or right.
Jo, profesor, se ke dy pjesë. Është pjesa që po të filmon është dhe kjo e presenting. Kjo që po të filmon ty është në rregull. E tregon pasë fare, mirë.
Okay, thank you very much for the note. I hope everything does better now. So you just flip the correct screen. Okay. So yeah, I think now I get what your problem is. Sometimes when I see myself, yeah, I see the flipped version. But let's go on. I hope now you get a better feeling of what's going on. So let's assume that we have this example here, which is this polynomial. And when we are trying to deal with this, to find the roots of polynomials, we are trying to, sorry, I have this here. It's probably the simplest set of functions that we can work with. And the first thing, when we try to find the root, we try to bracket it. And with bracketing, we just mean that we try to find a region where we have the sign change of a function, assuming that the function is continuous, because if it's continuous, if the function goes from negative to positive, we have a root. We should have a root over there, as we might be intersecting with the x-axis. Now, this is the function, and in order to do the bracketing, what we can do is that we can evaluate the function So we have the x here, we have the function f of x, and we evaluate this one at 0, 0.5, and 1.0. Okay, so we evaluate the function at these three values, and then once we see a sign change, we can do finer readouts. Okay, so here, for example, if we evaluate this one at 0.8, the function is minus 0.888. If we evaluate this one at let's say 0, we get a 5, which means that here we do have a root. Then we can have smaller steps to evaluate the function. I did some part of this for you, and I strongly suggest you can even follow the same. But if you keep evaluating, so the first thing that we can always try is to plot the graph. If we plot the graph of the polynomial, we can get there. So assume you are in a course, you need to find a root. You plot the graph, you see where the solution could be, where it's intersecting with the x-axis, and then you try to do the bracketing. And after the bracketing, after you define where the root can be, you start bracketing, dividing by 2 each time. Now, in this example here, if you see from this slide here, it looks like we do have a root between 0.6 and 0.8. So x, it's or the root, it's 0.6 to 0.8. That's what we are going after. You can see this one from these evaluations. And then, in order to plot this one, this is what you can try to do. And then, after we decide or we determine where the root can be, we go after a certain solution method, where one of them can be Newton-Raphson method. To find the root of an equation using the Newton-Raphson, we can find the derivative with respect to x, which is 3x squared minus 20x. So this would be the derivative. And then the iterative relationship that can be used to find the root is going to be xi plus 1 is equal to xi minus f of x divided by the derivative of f of x. Okay, so that's what the 3x squared minus 20x, that's correct. So if we start with this one, we can initially start with x1 equals 0.8. So this can be 0.8 minus 0.8 cubed minus 10, 0.8 squared. Sorry, this is not the whole thing. We get also a plus 5 here over 3 times 0.8 squared minus 20 times 0.8. And with this first attempt, from 0.8, you can get to a better root, which is 0.7. So,
Professor, I'm
yes,
sorry to interrupt you.
Sure, yes.
We cannot see the full table.
I
What
guess,
you are writing, it's not very clear.
okay.
You have to put the phone.
Okay, I thought I was in an acceptable range of writing. Let me double check myself. So it looks like you are not missing much actually. So you are not missing much, just to confirm. But if the resolution is not the best, please do remind me. So thank you for letting me know. But actually, this problem, this is also in the handwritten solutions that is provided to you. But this is, I guess, it's a different exercise. So this is a different example. Okay, but regarding this problem, we can start from 0.8. We can apply the first iteration using this expression that is shown here, where you need to evaluate the function at 0.8, and then the next value it's 0.736, and if we apply this 0.736 as in the next 0.736, we substitute this one in this expression, which is used for the Newton-Raphson method, and the answer that we get is 0.73. 0.7346. And then if we use the error calculation, where the error calculation is written as the approximate error. This is going to be equal to xi plus 1 minus xi over xi plus 1 times 100%. We figure out that with a couple of calculation of inserting this 0.8 into this expression, we get this. And inserting the 0.736 into this expression, we get this value. And it looks like we are not, these two values are very close to each other. And if we use this expression, we notice that with 2 steps, the error that we get here, it's something like 0.3%. This is the approximate error. This is 0.3%, which is a pretty decent work for a couple of calculations. So this is how we can find the root or improve the root of such a function. Now let me have a look what we have here with the model. That's something else. Okay. This example, I think it belongs to the next one. And now this polynomial, which is on the board, which is x cubed minus 10x squared plus 5, if we plot this on a wider range, we can see that we have the intersection with the x-axis or with the y equal to 0 line. We intersect this at 2 different points, okay? And if we have a look, it looks like we have another root. It's somewhere for values smaller than 0. That's correct. So we can search for a different root if we start at a different range. Starting here at 0.8, it helps us to converge at the root which is somewhere above 0.5 or 0.7. But starting for values smaller than 0, most probably this is going to converge to the next root, which you can track it down from this figure that you see here on the slide. Now, let's see, let's have a look at a different problem, and you can follow me on the, I guess, if you look at the slides, at the PowerPoint slides, at the last 7 or 8 slides, you can see the notes, all of these problems solved already. And I want to remind you that the Taylor series expansion, it was written as the derivative of a certain function evaluated at some point over n factorial x minus x0 to the power n. Okay, so let's assume that I guess at this moment I don't need much of the slide. I just want I guess now you see the board, right? Most probably you are. So in this function, for a moment, we just assume that x0 is equal to 0. So let's assume that you are doing the expression of functions with respect to point 0, which is also called the Maclaurin expansion. And if we set this x0 equal to 0, then this x minus x0 to the power n, this is simply x to the power n. And now let's assume 2 functions, okay, just as a small exercise. Let's assume that if we have the function e to the power x, this can be approximated as the 0th order derivative of e to the power x. It's e to the power x, the first derivative. This is also equal to e to the power x. So this is 0. E to the power x to the first derivative. This is also e to the power x. E to the power x, the second derivative is the same thing. So if we evaluate these at x0 equal to 0, because this part that we are drawing here in red, these are these, okay? So all of these functions, if we evaluate this at x equal to 0, we all get 1s, okay? This is also 1, this is also 1, which is going to be this part in red. And all this, because we always have to evaluate this at x0 equal to 0. Then each of these terms has to be divided by n factorial. So here we get 1 times 1 over 0 factorial. This is times 1 over 1 factorial times 1 over 2 factorial. And then we need to multiply these terms also with x to the power n. In this case, as we said, since the x is variable, x0 it was a fixed value. So here we get here x to the power 0 is just 1, okay? And x to the power 1 is x times x squared. So the first term, we get 1 over 0 factorial, this is 1. This is equal to x, and this is equal to x squared over 2, okay? So here we have the first three terms of e to the power x expanded with respect to x0. So e to the power x, we can write this one as 1 plus x squared over 2, okay? I hope this part is clear. The Taylor series expansion of e to the power x. Now, let's assume a different function, which is e to the power x squared, okay? So this is e to the power x squared. The zeroth derivative of e to the power x squared, it is, I guess I can use this part of the board, so we have e to the power x squared. The zeroth order derivative, this is the same function, okay? So this is going to be e to the power x squared, no changes. But we need to evaluate this one at x0. So e to the power 0 squared, it's e to the power 0, and this is always going to be equal to 1. Then we take the first derivative of this term, so e to the power x squared. The first derivative is equal to the function itself, okay, because we know that e to the power u, the derivative of this function, it's equal to the function itself, because e to the power u, it's always the same, times du over dx, okay? And this is going to be equal to e to the power x squared. U, in this case, is the derivative of x squared with respect to dx, and this is equal to e to the power x squared times 2x. So here, we can write that this is 2x times e to the power x squared, okay? So this is the first derivative. Then the next thing that we need to do is do you see the board better? I just had to close the window. Can you see the board correct? All right now? Yes, okay, just thanks Kevin. So let's continue here. So the first derivative it was equal to this expression. Then we go on with the second derivative, e to the power x squared. Second derivative is going to be equal to what? The second derivative is, we're going to have we find the derivative of this term. So we take the derivative of the first term times the second one. So let's assume we have two functions, f and g. The derivative of 2x, it's 2 times e to the power x squared plus 2x times the derivative of e to the power x squared. The derivative of e to the power x squared, it was this function here in red. So this is the derivative of this function. We multiply it by 2x. So this e to the power x squared times 2x times another 2x, this is equal to 4x squared e to the power x squared, okay? So here we can redo this part, e to the power x squared, to confirm that this is correct. So it looks like zeroth order derivative, the first order, the second order, this got 1. And now let's substitute here, what is the value of this function? And let me remind you, this in red, these belong to this part of the Taylor series expansion, okay, where all of these, they are evaluated at x0. So this part here, we have a 0, which is 2x, which is 0 immediately. So here we get a straight 0, okay, in the Taylor series expansion. Then we come to this part, we get 2 times e to the power 0, we get a 1 here. This part, it will be 0 because we're multiplying the whole thing with 0. The surviving terms are only exponentials to the 0, which in this case, this is going to be equal to 2. Okay, so that's what we get. We can follow one further step. We can try to find the third derivative of this function, because this is how we should progress. So this e to the power x squared, the third derivative, and the one last step, it would be the e to the power x squared, taking the fourth derivative of the function, and we will have to follow the same steps. Now, assuming that this part we are relatively clear, allow me, this was the e to the power x expansion. And before I erase this, one thing that we can do is that we are saying that e to the power x, actually this is not equal, this is approximate. So now we can do the following, e to the power x dx, we can integrate this one, okay? And similarly, this would be approximate, of course. We should have that 1 plus x squared over 2 dx. I know that this might become a little confusing, but here we see a red line separating what you have. So if you are asked to find the integral of e to the power x with respect to the variable x, you can in fact use just this 1 plus x squared over 2 dx. But one thing that we need to keep in mind is that we are doing this expansion as long as this x that we see here is in the proximity of 0. So if we're integrating expressions that go from 0 to some epsilon, assuming that epsilon is relatively close to 0, even in order to make sure or to double check with ourselves how good the Taylor series expansions are, you can even make this epsilon 1, okay? And you can calculate how much the errors could be. So even if you go from 0 to 1, you could get approximate or relatively accepted values. Now, this part of e to the power x, we can erase this part, and let's try to assume that we want to evaluate the integral of e to the power x squared if you want to take the integral from 1 to 1 over 2, okay? And this is e to the power x squared dx. This can be written as the integral of, let's pick out the first 3 terms of this function. But actually, let's try to improve what we read here for a moment. This is the 0th order derivative. We look at the Taylor series expression, we have to multiply this one, 1 over 0 factorial, times x to the power 0, right? And this whole thing, it's equal to 1. That's the first term in the Taylor series expansion. The first derivative here is 0. We multiply 1 over 1 factorial times x to the power 1, but the whole thing is 0. And the last term, we have to divide this one with 1 over 2 factorial times x squared. So this is the x squared. And I think you wrote this one. I can erase this for a moment. So in the Taylor series expansion, this corresponds to n equal to 0 term. This corresponds to the n equal to 1 term. And this is the third term corresponding to n equal to 2 term. This is how we are doing these expansions. And then it looks like the first 3 terms, we get 1 plus this other term here, which is 1 plus x squared dx. This should be approximately equal to this term here. Now, if we this part, we could erase it for a moment, and if we integrate this one, the integral of dx is equal to x plus x to the power 3 over 2. From 0 to 1 over 2, this is equal to 1 over 2 plus 1 over 16. Okay, so this is the integral. Yes. You have a problem?
Should it be over 3 integral?
Yes, you're right. That's right. It should be x cubed over 3. Thank you for letting me know, but still, it's not correct. This is 1 over 2. Yes, that's correct. If this is like this, we should have here, this is plus 1 over 3, and this is 1 over 2 cubed. So this is equal to 1 over 2 plus 1 over 24. Okay? So we get something more correct here. And this would give to us 0.
Professor,
Yes.
mund ta hapni tek kamera sepse del mbrapsht.
Po sigur të ndroni, unë kam përshtypjen se dikush nga ju e përmendi këtë gjë që juve ju shfaqet dy ekrane. Shikoni te ekrani.
Edhe mua.
Ë?
Edhe mua më shfaqet në 2 ekrane, sepse keni
O
hapur
Bjorn,
këtë
shkote
pjesën e presentation.
people. O Bjorn, shkote people, bëj pin profesorit.
Okay.
Okay, things are better, but it's good to go over these. So this is 0.54 and 167. Okay, so this is the result that we get from integrating just over 2 terms. And this one, it gives us an error, a total error of approximately 0.6%. Okay, so this is the error. This is the true error where we find the relative error of this value that we found, 0.54167, with respect to the exact root or exact integral result from this term. Now, if we take the third derivative of this function and we evaluate this at x0, we find that this whole thing, it will be equal to 0. Okay? Because once you take the odd number of derivative, you always get x to the power, we get some x's everywhere. And I can, so this will be a 0 overall, once we evaluate this one at x0 equal to 0. I'm talking here for the third derivative of this function. The fourth derivative, it's going to be equal to
12.
It's equal to 12, that's correct. So it's going to be equal to 12. But then this 12 is going to multiply. So this is n equal to 0, this is n equal to 1, this is n equal to 2, n 3, n is equal to 4. So we multiply this one with 1 over 4 factorial, which is 1 over 2, 3, 4, times x to the power 4. So we can cancel out a few terms, and we get something like this integral of e to the power x squared dx. This is can be approximated. Sorry, this is approximate sign. This is 1 plus x squared plus x to the power 4 over 2 dx. And if we substitute this, the value that we're going to get for the 4 terms is going to be a value of so this is the answer, which for sure it's more closer to the previous value with respect to the first approximation. And here we get an error of 0.03%. 0.035%.
Po, profesor, më fal.
Yes.
Bërë një pyetje. Pse marrim këto vlerat 1, 2 dhe 0 për integralin?
Sepse ne po mundohemi në thjesht shembulli këtu është që ne duam të gjejmë sa është integrali n fuqi x katror dx nga 0 deri te 1/2. Kaq është ajo që po mundohemi të bëjmë. Okej, ky është shembulli, po mundohemi të parafërsojmë një vlerë të një funksioni. Tani shpresoj të shikoni këtë. So if we do something like x is equal to ln space from
Question mark.
from 0 to 0.5, and if y is equal to exponential
Question mark.
of what is this, x squared, right? This is x squared
Question mark. Question mark.
Okay, so here we have the function of e to the power x squared, which is shown here in this figure. Let me try to, I'm trying to make it so you see much more than you do. So apparently this is the e to the power x squared function. And we want to find the integral, which would be the area under this curve. So that's the problem, okay? And now we are saying that, and also we hope to integrate this one up to here, and we hope to get close to exact results, because we are expanding around the 0. If this number, it gets larger, the error would be larger when we compare the exact answer with the approximated one. Because we always know that whenever we take the Taylor series expansions, the values that we get, they are all approximations, okay? So, is it clear?
Papa,
Okay, that's good. So this function, which is that we see here, that you see the plotted one, we're hoping to approximate it, and that's what we get. Okay, so we can go to another example, and we have an example here, which I find it. I hope you'll find it. We'll learn something out of it. So we have. Now, in the couple of examples that we are going to cover, there are some. The problem is defined as follows. So, if we have a water tank in the shape of a sphere, what is going to be the volume? Okay, so we need to take an integral. The integral, it's on the lecture notes. You can go over those, but the volume. Let me find it in my notes. Probably so if we have a water tank in the form of a sphere, the volume here, assuming that this is h, this is the height which is filled with water, this is h, this can be the radius r of the tank. The volume is equal to pi h squared over 3r minus h. Okay, so this is the expression of the volume, and then the question that can rise is the following: assuming that the radius is 3 meters. So given r is 3 meters. And the volume of water that we need to fill, this is equal to 30 meter cube. So if this is also 30 meter cube, find h, okay? So h is what? So in this case, we have a function that whenever we ask the question, find the h, this is like finding the root. Because if we substitute some values here, we have, if r is 3, we get here, we get the volume. Oh, we know this volume, this is 30. So let's substitute the values that we know, and let's see what we don't know. So this is 30, this is equal to h, it's unknown, so r is 3, and we get here 3 times 3, 9, divided by 3, 3 pi h squared minus pi over 3 h cubed. Okay, so this is the, if we multiply by 3 everywhere, we get a function of h which is equal to 9 pi h squared minus pi h cubed minus 90. So I just take this 30 to the other side, and now this is a function which depends on h, but we want this one to be equal to 0 because this is 0. So the question was find h. So this problem, it comes down to root finding problem. Now, what is the best, one of the techniques that we can use to find this is to use Newton-Raphson technique. And actually, maybe one of the fast ways to calculate this one is, let me see if I can find it around here. No. This is 9 pi. Okay, so I think this is the example. So probably you don't, if you, I guess from the shared screen, this is 2.03. So this is the, if we start solving this, we get here f of x is equal to 9 pi x squared minus pi x cubed minus 90. Then the next, the derivative of this function is equal to 18 pi minus 3 pi x squared. So we need the function and the derivative of the function to find the, to use the Newton-Raphson method. Actually, what I've shown here, this is the f of x. I hope you're seeing now my screen here where I'm just writing something on Excel. So this is the derivative of the function because that's what the formula I have used. And this is equal to the first column minus, so we just can use this one, xi plus 1 is equal to xi minus f of xi divided the derivative of x of xi. So if we start with x3, we observe that we end up into 2.3. If we start with a value of 5, it looks like, let's see where we go. If we start with x5, the error, oh, we need to do some more steps apparently.
O profesor, të derivati është 18 px.
Po këtë drejt. Kjo ishte gabim, 18 për x minus, po kjo pjesa tjetër besoj është, I think it's correct, it's 3 pi x squared, yes. So now, I just switch here to Excel because it's, we can also write the code about this one. Probably it's better if we move on this side. So if you run this one on any programming language, you could, let me try to find where I have it. So if you want to use, we can use the Newton. So to run a programming code, we need to define a function. Can you see my, I guess you can see my screen, right?
Yes.
Okay, thanks for confirming. So we can use a function. This is Octave Online or MATLAB files. And these files are included in the lecture list of notes. So for this one, to run this code, we just need to write, first of all, the function. And the function...
Question mark.
The function, we write this one as y is equal to, what is 9 pi x squared. This is 9 times
Question mark.
3.14. Allow me to use this notation, 3.14 times...
Question mark.
Sorry, my computer wants to do the dictation. Question mark. This is 9 pi times x squared times
Question
x
mark.
squared minus pi x cubed minus 3.14 times
Question mark. Question mark.
Question mark, question mark. Cube minus 90. So here we get the minus 90. So this is the, and we save this one. So that's the function that we need. Then at the same time, we need to determine
Question
or
mark.
to provide y is equal to 18 pi x. So this is 18 times
Question mark.
3.14 times
Question
x
mark.
minus 3 pi x squared minus 3 times
Question mark.
3.14
Question mark.
times x squared.
Question mark.
Yes, it is. Okay. So here we get the, we save these two functions that we need. Then we can go to this this function, which is the Newton,
Question
which
mark.
uses the Newton-Raphson method. And when we run it, first of all, we need to define here, so the function, this is going to be the function fun1, because we saved it in the function. Here we define the derivative of the function. This P0 is a point where we start. So here, it is this point. Probably already know if I switch now between the screens. Let's see what we do here. This P0, let's assume that let's start something like 2. If we start this delta, this is the error in the x value. We just press some 10 to the power minus 3, 10 to the power minus 4 values, okay, just to check them. We can even try 0.001, and this is the maximum number of iterations that you can allow. Let's assume that you allow just 5 iterations, and it looks like we get an answer. Can you confirm, can you see my screen?
Yes.
Okay, thanks. Okay, so it looks like we started with a value of what? We started from 2, and it converged to a root, which is around 2.075. Okay? So we started from 2, we went to 2.075, and it did this one with 2 iterations. So when k is 2, just running this one twice, it got to this value with a precision in the value of x with whatever we wrote. If you look over there, it has a precision of 10 to the power minus 4. That's why this P0, it gives us 4 significant figures after the comma. Now we can run this again with adding 2 orders more precision in x and y. Let's see what we get. Yes, it looks like it does converge very fast. So with 2 iterations, we still get the same thing. The error is much smaller. I guess maybe we can experiment with this one a little further. Okay, so here we get just one more k. So k now is 3. With 3 iterations, we get the correct result. So that's what we get. But now you can also start with different values. So we start with 2. When we try this with 5, probably I feel that we need more iterations. Okay, so if we start with the value of 5, we need 5 values of k's. So the k equal to 5, we run through 5 iterations. Let me check here. That's not a lot, 7. Oh, we still solved it. I was hoping not to get a convergence so fast, but let's get here to 22. Okay, yes. No, actually, if you see here, we get a different solution. For the last, when we're trying the 5, 7, and 22, the solution that we get is like 8. It's not 2 centimeters, but it's 8.6. And let's check if it makes any sense with our results. So it looks like to fill this one this much, if the radius is 3 meters, that means that this is 6, okay? And the h, it was 2.03 or 2.075, sorry. So it looks like this is going to be filled like a third of this height, okay? And now it looks like the Newton-Raphson method, it gives for us, which means that this function, it has, actually, let me ask all of you, how many roots should this function have? Can I get an answer from you? But in order to get an answer, you also deserve to see the screen. So my question was this, apologies. So this was the function that we were trying to find the roots. How many roots can this function have?
Maximum 3 roots.
Sorry, 3. Okay, I got a couple of answers from you. Silvana said this should be 3. Yes, we are going to expect 3 roots because this is a polynomial of third order in H, in the unknown H or unknown X. So it looks like, but it's also imperative. It could be easily expected from us that we should have only one, okay? So we should be a little careful. So if we randomly select the starting points for the Newton-Raphson root, 2 of them are the French. Yes, you are correct. So I got also a couple of more comments from Ariod. So in principle, we can get 3 roots, but only one of those would make sense, okay? The other roots would be something out of range, which in this case it was like 8, which means that this is going to be filled with a lot more water, okay? Now, this example, it was related to being able to fill a tank in the form of a sphere with water. Now, if you follow the lecture notes that I've shared with you, the next problem that we can go over is to have a piece of wood cut in a shape of a sphere, and we drop it on water. But since wood has a smaller density than water, we expect it to stay somewhere like this. Okay. So now this problem of having a tank filled with water, assume that this is a piece of wood. The water has some density rho, which is 1 gram per centimeter cube, and for the wood, this is something smaller than 1. Okay. Now, if this is the case, the function that we will have to deal with, it's going to be something different, because the volume, now this H, that here it was considered for the amount of light which will be filled with water, we can assume this one, the amount of the y distance that the piece of wood would cascade into the water. So now, this is also the volume that will be displaced, the volume of water that will be displaced once you put an object. There is a law which states that the force exerted on any ship is equal to the weight of the water it displaces. If that's the volume, we just do the rho of water times the volume that it displaces, which is going to be this volume here. This should be equal to the mass of the sphere, which is rho of wood, the density of wood, times 4/3 pi r cubed. So the complete volume of a sphere times its density, this is what we get. If the units are in centimeters, we can consider that the rho of water is 1. Okay, so we get here this volume that is shown here. Let me call this one displaced water. Displaced water, H2O. This is what it is. We insert 1. We get here pi H squared R minus pi H cubed over 3 times 1. This is equal to rho of wood times 4/3 pi R cubed. So now we have some terms that we can directly cancel out. We can multiply every side by 3. This cancels out, this cancels out. So we get a new function. And this function that we are going to get, if we set the rho of wood 1/3 of water, so let's assume that this rho of the piece of wood has a density of 1/3. If we substitute everything here, the function f of x, this will be something equal to 30 h squared minus h cubed minus 133.3, and this is the case when the radius is equal to 10 centimeters. So if we use this this r, this radius for the piece of wood, that we drop it on water, if we want to find how deep this goes into water, we have this equation, okay? And we need to find where the zeros are And if we want to use the Newton-Raphson method, again, we need to find a derivative. The derivative is going to be something like 60h minus 3h squared, and so on. So let me give some more space. So this is how we can try to solve these types of problems. I think you have this one solved on the lecture notes, so I hope you can go over those. And other important aspects that we can discuss. We have actually, I got a couple of comments here, which I can I just had to read. As 3 roots, we are allowed. Yes, okay. So it was regarding the question I asked before a while. Now, fixed point. Now, other than the Newton-Raphson method that we tried to solve a couple of times, I just want you to go over, and in the meanwhile, nëse keni ndonjë pyetje, unë do ju lutesha të më pyesni. But I take from you that most probably you have seen the homework posted, but I just want to. It is better now. Okay, so probably when I switch from one screen to another, I hope this is a better quality now. So now in the homework, that for the sake of getting to, I think also here in the PowerPoint, I think I try to make it clear that the homework 6-point iteration. So here we have what? Actually, it will be really good if we talked about the convergence of systems. Okay, so if you remember from last time, we said that among the different techniques that can be used for root finding, fixed point iteration, FPI, it was one of the techniques which used to converge if the slope of the derivative of the function was had an absolute value smaller than 1. Okay, so last time we drew such a function where the objective was to show that if this is y is equal to x, if the slope of the function is smaller than 1, where the root is, then we can find the solution. Now, actually, I think it's clear also from this graph. Okay, probably I can better go over in the slide here. So this function that we have at this moment, I've drawn this one, and I've drawn, which is seen here, but the quality, the lines are not very visible probably. You can try to draw them on your own. But this is a polynomial of second order. We want to find the roots. Question is, can we use fixed point iteration to find the root of this one? In order to figure that out, what we need to do is that we look at the derivative. The derivative of this one, it's 2x plus 1. And this 2x plus 1, we evaluate this derivative at the two roots, at x minus 2 and x equal to 2. If we evaluate the derivative of this function that we want to find the root of, we see that the derivative, it will have values of minus 3 and plus 5. Now the absolute value of, now this minus 3, it's something which is like a huge slope, but it's a negative slope. So this minus 3, in principle, at the roots, so this at the huge slope is going to be something like this. If we evaluate this derivative at x is equal to 2, the slope is going to be something like 5. The slope is much higher. Now, this slope of minus 3 and 5, the absolute value is much more than 1, which means that we cannot find the root of this simple polynomial, x squared plus x minus 4, using the fixed point iteration. I said FIP, that's wrong, misspelled. It should be, the acronym is FPI, but it's not that essential. So we have to be careful. Now, let's have a look at this other problem here. The function is x cosine x minus x. let me try to have a better look here, but probably you can also see from here. So if this is the function x cosine x minus x, the question is how can we find the root? Can we use the fixed point iteration? X cosine x minus x. Now, the root of such a function, it's something like, let me have a look. So the root of this function, we know that we mean this. Whenever this is 0, when is this 0? When x, this is cosine x minus 1. This is 0. So it looks like we are going to have a root whenever the cosine is 1. Now we know when cosine is 1. Cosine is 1 whenever we are, this is cosine 1, okay? This is cosine minus 1. So whenever the angle is 0, 2 pi, 4 pi, this is when cosine is 1. Here, cosine is 0. Cosine here is also 0. So it looks like we have an infinite number of roots for this example. But now I want from you to solve this problem. And actually the first question is, can fixed point iteration be used to solve this one? I want you to go over this, and you can also go over the lecture notes. You have the answer there. I hope it will be a good exercise. Then the next question is, can you use the Newton-Raphson method to find the root? You can also use the codes that are provided. If you want to use MATLAB or any other programming language, you can also write down the code in any other. You can write it in Java or C, C++. But then, as a homework, I just want you to see what happens to the value that is found using NR, using Newton-Raphson. If we start from x0, from 0 to 6. So here, assuming that we are starting from some x0 equal to 3, where does this converge? If we have x0 equal to 3.2, where does this converge, and so on? Let me see if I have a figure here. No, apparently I don't. I thought I had. Okay, but let's stay here. And there is probably, let me have a look here. Since the screen is shared. And by the way, let me try to identify where I have this one. This is 30. No, I should have something relating the sines and cosines. Okay, so I just wanted to demonstrate something fast, but probably it's best if I really cannot find it. Okay, I thought I had it. But my question here is the following. I want you in the homework draw a graph of so let's say the values of convergence for you, they should be something like 0, 6.28 for the unknown here, okay? Then you should get something like 4 pi, which is 12.56. So this should be the values where you should converge. But now, if you are searching from 0 to 6, 0, 1, 2, 3, 4, 5, and 6, so from 0 to 1, probably the convergence should be 0. Okay, so you get some points here. When this is 2, if the problem converges at 6.28, you should have here 6.28. So probably it converges like this. Okay. If you change the value of x again, you might find, some of you might find that this is going to converge at 12.56. Okay. So the graph should be something like this. So I can ask you to draw this graph, which is a function of x0, initial value of the you are using for the iterations, and the final answer. Or you can also draw the graph of x0 versus n that you can see in this slide. In this case, you can assume the following. N is equal to 0 when this is 0, n is equal to 1. So in principle, this n is x0 over 2 pi. So, so this n, this is equal to x0. I hope you are seeing this. This is sorry, this is n is equal to x divided by 2 pi. Okay. So this is what I want you to draw, these two graphs. I'm going to save this one. And the same thing you're expected to do also for y is equal to cosine x. You have two new homeworks. I hope it will just be a good exercise for you to see what happens with the Newton-Raphson method and how the convergence plays across. Now, the time is it's past 12:30. I have to, because of the curfew that we have, the military curfew, I might have to end the class, but you are responsible to go over all the material that you have received by PowerPoint in the Google Classroom. Some of them, actually, mainly the major information is in the handwritten notes. So I think you can, I'm using the university facilities for now, which means that by 1 p.m. I have to get home. If you have any question, you can ask, but until next time, you are responsible to read the chapter on optimization. I try to explain as best as possible on the slides and on the lecture notes. So you should go over chapter 7. And until next time, we'll start solving linear systems of equations, which you have covered them in linear algebra. I'm sure you did a good job in there. And here, in this course, we're going to use other techniques how to solve them. Meanwhile, any question? You might have if you have any question regarding the homework, please you can email to me. Homework is posted on LMS, I think, and also on Google Classroom. You can confirm. Okay. Okay, if there is no more questions, I thank you for.
Ku duhet ta bëjmë detyrën?
The homework, you could solve this one with your handwritten. You can write it on a Word text, but probably the best thing, you can do it handwritten. You can you can scan them or take photos of those, and please merge them into a single file. Don't try to not submit 5 pages where each page is like 5 megabytes. So if you take pictures using a cell phone, do not. You can submit them either on submit them here on Google Classroom, okay?
Or programet mund të çojmë tekst?
Sorry?
Programet që do shkruajmë për të bërë iterations. Mund të çojmë tekst?
Po, ato bëni include them in the homework, yes.
Okay.
Programin përfshiheni.
Profesor.
Okej,
jepi ti.
Vazhdo, Xhulia, vazhdo.
Profesor, po slide dhe këto leksione që i bëni rekordin, mund të na i çoni do?
Po patjetër, unë herën e kaluar atë slide-in, të videon e kemi bërë share, linkun e YouTube-it e kemi dërguar gjithë në klasë. Nëse se ka marrë dikush, mund t'ja dërgojmë përsëri ose mund ta postojmë tek edhe këtë leksion e sotshëm mund ta shihni edhe më vonë.
Okej, vetë pashu postojni në LMS ose në Google Classroom recording bashkë me slide-et që dhe ne t'i hedhim një sy përsëri në shtëpi.
Dakor, patjetër, po do postoj. Do vendos linkun e YouTube-it. Në rregull.
Okej.
Në qoftë se s'ka gjëra, ju falenderoj për gjithë dhe për çdo problem që mund të keni gjatë këtij procesi, ju lutem me email me çfarë do lloj mënyre mund të më kontaktoni, dakor?
Profesor, mund të bëj një pyetje?
Patjetër.
Për shkrimin e një detyrave të shtëpisë, ju doni që ne t'i zgjidhim edhe me anë të kodit dhe t'japim shpjegimin për kodin në fletore të shkruar apo?
Që të jem sinqert, se mbaj me çka ka qenë detyra e shtëpisë ushtrimit i parë, por këtë pyetjen tënde ta marr me vete unë të thej përgjigje me email.
Okej, profesor.
Në rregull, se më duhet të dal pa më kap trafiku te mbi kalimin. Mirë, pa faleminderit edhe një herë për gjithë për vëmendjen. Keni qenë në numra të konsiderueshëm për sot. Atëherë mirupafshim deri herën tjetër.
Po, shumë mirë.
Mirupafshim. Faleminderit.